Hello, so this is a preview screencast for session 15, where we're going to start looking at lamina, composite lamina, so individual ply properties of a composite. And we're basically going to build on what we did previously, where we were looking at the constituents. So we learnt in the previous session on composites that the individual fibres of carbon or glass or Kevlar have enormous properties, enormous specific properties compared to bulk metals. Now, we can't realise those full properties into a real composite because it's not all fibres, there's some matrix in there as well. And what we're basically going to learn about in session 15 is how to convert the fibre properties into the properties of an individual ply. So a ply, or a layer, or a lamina, these are all the same things. It's basically one layer of a composite material. And it's very important, because the properties of composites are anisotropic, they're not the same in each direction, that we define some material axes and some terminology so we know which properties in which direction we're talking about. So for a unidirectional ply like this, where all the fibres are in one direction, we usually define the one direction as the fibre direction. And the two direction is the transverse direction, and the three direction is the through thickness direction. If we've got a woven ply, then we'll pick one of the directions to be the weave, and we call the other one the weft. And the weave direction is 1, and the weft direction is 2. In principle, you can have woven forms that are anisotropic, so there might be more toes in one direction than another. So that will have slightly better properties, and therefore the one with more toes is conventionally called the weave direction and called the one direction, so we're consistent. The rule of thumb is that the one direction should almost always be better than the two direction in terms of its strength and stiffness, except if you've got a woven composite where there's equal number of toes in each direction, in which case they'll be the same. But the properties of the one direction shouldn't be less than that of the two direction. So what we have to do, because it's an anisotropic material and because we've got different directions, is define lots of different properties for the lamina. And these are the properties that are generally most important for design. So we've got a longitudinal modulus, so a modulus in the one direction, which we call E subscript 1. And in principle, that modulus can be different in the tensile and compressive directions. Often there isn't a significant difference in modulus, but if we want to be able to describe things completely, we will call 1T and 1C. Often these are taken to be the same, which is E1. We've got a transverse modulus, E2. Again, in principle, that could be different, but in practice, it's often considered the same. We've got longitudinal tensile and compressive strengths. These almost always are different, so it's important to have separate subscript T and subscript C. And the notation I use is to use a little star here to indicate that it's a strength rather than just a stress. We can have a transverse tensile strength, we can have a transverse compressive strength, so a strength in the two direction, in tension and compression. And then we've got an in-plane shear modulus and an in-plane shear strength. For most laminate analysis, we don't consider the through thickness direction of strength in any great detail. Okay, we tend to work in plane properties only, because composites tend to be used in thin sheet form. The basic method by which we can convert a fibre and matrix property into a lamina property is called the rule of mixtures. And it's a very useful method, but it still can't predict everything. So what we have is basically a method that we can work out the modulus, E1, as basically a sort of weighted average of the modulus of the fibre and of the matrix based on this thing VF, which is the volume fraction. So that's the proportion of the solid that's made up of the fibres. So typically for a unidirectional system, this will be about 60%. And we can also use this equation to work out a strength as well. It's not such a good estimate for longitudinal tensile strength, but it still allows us to gain an estimate. We can also use a similar method to work out the properties in the transverse direction. We can derive an equation for the transverse modulus, E2, which is dominated by the matrix properties. It's not such a good estimate, but it is still a way of estimating this property. So what I'm going to get you to do in the session is to use the example of a high-strength carbon fibre epoxy matrix and to basically work out some typical values, and we'll discuss that in the session. The rule of mixtures is a really good way of providing first estimates of laminar properties if you haven't got any better data, and we should never underestimate the value of a nice simple analysis like this. For real design, however, we'd use actual property test data that we obtained from tests. But the rule of mixtures is still really important and really useful for scaling test data to allow for small variations in volume fraction. In terms of failure modes of laminar, the two important ones that we're going to look at are the longitudinal ones in tensile and compression. And the reason these are very different is because their actual failure mode on a micromechanics level is very different. And I've got a couple of quick animations to illustrate this. Tensile failure of a composite is dominated by the fact that the fibres, the strain to failure of the fibres is usually much lower than the matrix because they're stiff and brittle. So the mode's dominated by fibre failure. It's also dominated by the fact that fibres have a statistical variation in strength because they're brittle. So what you have is basically a failure mode where small failures in the fibre kind of collect as the load increases. And in practice, as individual fibres fail, they load the adjacent fibres and the matrix, and eventually you get an overall failure, usually with the fibres sort of looking like they've spread out. It's sometimes called brooming. In contrast, the compressive failure is basically driven by buckling of the fibres on a micromechanics level, and it's often known as compression microbuckling failure of the laminate for that reason. Here are some examples of what the actual properties of a unidirectional ply and a woven ply really are. So you can compare these with the values that we've calculated using the rule of mixtures. The important thing to notice here is that we've gone down from fibre moduli of over 200 to a value of 140, which is still very good. It's significantly higher than titanium, not quite as high as steel, but we know it's much less dense. And we've got very good strengths as well. 2000 megapascals and over 1000 megapascals for strength and compression. The properties in the transverse direction in terms of strength and stiffness are very much lower, which is what we'd expect. Typical volume fraction for a unidirectional ply will be up to about 60%. For a woven ply, we can achieve a slightly lower volume fraction because the weave has to go under and over each other, and that makes it difficult to kind of pack as many fibres in. And the key thing about a woven ply is that the properties in the 1 and 2 directions, in this case the weave and the weft directions, will be the same. So that has some advantages but also some disadvantages. You'll notice that the strengths are generally a little less than half the strength of a unidirectional. In other words, a woven fibre doesn't quite give you as good overall properties. And we'll go through all of that in a bit more detail in the session.